Hi, welcome back. In a previous video we were looking at the DC load for testing our power supply and things like that. We went through a few examples on a breadboard, tested a few things out, did some performance checks and everything, came up with a reasonably good circuit, certainly good enough for the power supplies we're going to be making, and almost good enough for even some of the high performance Agilent power supplies. We managed to get its transient response time down to a few hundred microseconds and things, which was pretty good. And we were able to either drive it from a 10-turn potentiometer, or we were able to drive it from an arbitrary waveform generator, which is kind of cool. Input voltage was basically 0 to 5 volts, representing a 0 to 5 amp range. And because of the MOSFET and things we were using, we were easily able to handle 30, 40 volts or even more of a supply, and currents up to 5 or more amps. Our design criteria is 5 amps though, so that's what I've stayed with. So in this video, what I'm going to do is I'm just going to complete the analog version of the DC load. Been busy with my 3D printer, and what I've done is I've created a front panel for it. I've got a project box which I showed in the previous video, which has got a little strip board in there with the circuitry all wired onto it, and I demonstrated the fact that I had an old CPU heatsink which I bolted to the back. It's got a fan on it which is being driven from the 12-volt supply that plugs in the back. I've got a coaxial connector for the arbitrary waveform generator to feed in. I've left it in high impedance mode so I can choose whether I terminate externally with a 50 ohm resistor or whether I put in a high impedance signal. Either way, it's 0 to 5 volt input for that. On the front panel, of course, I've got the dual voltage and current panel meter, which has been hacked to allow the current side to be floating independently of the voltage measurement so it doesn't interfere with any readings. I've got a switch so I can switch between arbitrary waveform generator or the internal pot here, and I've got my banana jacks sockets so that I can connect my external device that I want to test, whether it be a power supply or a battery or whatever else it might be. Doesn't do logging, doesn't do anything fancy. It's just a straightforward 0 to 5 volts. Will handle 30 odd volts or more. So at 5 volts with 5 amps with 30 volts, that would be basically 150 watts. And I've actually done a test with this on the bench and left it running for nearly 24 hours at that full load. And whilst the MOSFET itself was probably getting quite warm, the heatsink with the fan going on it stayed very, very cool, barely above ambient temperature. You could sense slightly that it had gotten warm, but because the fan is here blowing all the time, it doesn't get very warm at all. So therefore, this thing is good for probably 150 watt load for quite a long, lengthy period of time, which is kind of cool. So anyway, let's have a closer look at what I've done, and we'll power it up and you can see it all working. What we have here is our N-channel MOSFET bolted to the heatsink. I also have my 100 milliohm shunt Kelvin resistor. It's from Vishay, which is also bolted to the heatsink as well. It doesn't get very warm, but I figured it's a good place to mount it anyway. I've got my 12 volt DC input up here. Now you can pretty much supply anything from 5 volts to 12, 15 volts, so it's pretty flexible about what you supply it with. Now obviously if you give it a lower supply, then your fan is going to work a bit slower, and I put a 12 volt fan in here on the back. You can disconnect it if you want, if you're just going to do some very low currents. Also, if you're going to run it on a low voltage, then you may be limited as to how much current you'll be able to get to. Not because of the 5 volt input, but because of how much above you can take the gate from the source in order to turn the MOSFET on. And then the last thing here we've got is I've got a short length of coaxial cable which is bringing in the arbitrary waveform generator up to the switch over here. So let me just rearrange this slightly so you can see here. So what we have is just balancing everything here. We've got the terminals at the bottom. I've got heavy gauge cables going down to the MOSFET and back again. So that's nice, bolted directly to the clamps. I've got my voltage sense soldered straight to the top of the terminal strip going up to the panel meter. The ground 0 volt reference is gone to the negative of the terminal, so that we're truly measuring the voltage across here, and it has no impact on the fact that the actual supply for the panel meter, which is this red wire, is going over to the strip board here and tapping off of the input from the power supply and after the smoothing. Just because that's different, because it's measuring the volts at the output, that little bit of discrepancy as the current goes up and down on the supply to this is going to make no difference, because it has its own internal regulator and voltage reference, so it's quite happy with that. The switch here is allowing us to switch between the Arbitrary Waveform Generator input or the output of our Ref02, which is this chip right here on the strip board. This one here is the op amp that we were using. One half is acting as a buffer for the Ref02 voltage reference, and the other half is driving the MOSFET. Now, I do have now some higher powered op amps that have a more drive capability, so they may work a little better to improve the response time for this, and if I get a chance I'll plug that in later and we'll give it a quick test. Meantime, everything else that's on here is pretty much exactly the same as you had already seen on our previous video when we had this running on the breadboard. The only additional thing that's on here, of course, is I've tapped the 12 volts off. I put it through a little ferrite bead that I had before it went out to the fan to try and minimize any noise that might kick back from the fan running. So hopefully, we won't see too much interference from the fan. And that's pretty much it. So let me just box this up and we'll power it on and give it a go. Oh, one quick thing. The strip board is the size it is because I just actually cut it to fit vertically into the case. So it just goes down here, and then when I screw the lid on, it holds it in place because of the slots on the side of the case here. A couple of terminal blocks so that I can easily disconnect it if I want to from the from the power, and that's really it. So it just plugs right in here and everything basically sandwiches down, and that's it. I've also put heatsink on as many connections as I can just to minimize the chance of anything shorting out, especially at the back here with all the wires and everything. So anyway, let's put it together, give it a go. Okay, so box is put together, set to potentiometer. So let's just wind this down to a minimum for the moment. What I've got is the 30 volt output from my Keithley 2230G power supply feeding in through a 1 ohm load resistor right here. I've put this in here so that I can actually use the oscilloscope to measure what's happening on the load here. I've then fed for short lead, high capacity lead into the front of the DC load, and the output of the DC load feeds back to the Keithley power supply. So this is going to get a little bit noisy when I turn on the DC load because of the fan in the back. So you'll have to forgive me for that. I don't want to fry my MOSFETs, and I haven't got a variable speed controller on it yet. Anyway, I've also got an oscilloscope hooked across the 1 ohm shunt resistor that I have outside here. I'd like to use the Tektronix MD03054 Arbitrary Waveform Generator as well, but unfortunately its Arbitrary Waveform Generator output ground is not isolated from the rest of the scope, which means that if I plug it in the back, I'm actually going to connect the 0 volts wherever I hook the scope onto to the 0 volts of the input, which completely messes up all of the readings, and I introduce some horrible ground loops and everything else. So what I'm going to do is I'm going to use my Agilent 33622A Arbitrary Waveform Generator to feed in some sine waves and square waves and stuff like that instead, which does have isolated outputs, so that allows me to use all of this kit in one go. The other thing we have hooked up here is my Keysight U1461A multimeter insulation resistance testing and everything. So that's our setup. So let's just now power supply's on, and I've set channel 1 to be 30 volts output right now. And I've set the current limit to 1 amp on the power supply. Actually, I'm going to set the power supply current limit to its maximum. That'll allow it to go up to 1.5 amps. I'll be setting it on here anyway, so I can take it up to 1.5 amps. So 1.5 amps at 30 volts, of course, is going to be 45 watts of power that will be dissipated in here. Marginally less because we're going to drop a volt here, so it's actually going to be 29 on here. So when you read the voltages on here as well, you need to remember it will read at 1 amp, it's going to read about a volt lower than what is being shown on the DC power supply for its output. So let's power this thing up and we'll give it a go. and turn the power supply on. The output set. Right off the bat, you can see here, see if I can tip this DC load up a little bit so that you can see the display a little easier. Actually, I don't need to show everything, so I'll zoom in a little bit so you can see better. There we go. So I've got 30 volts on my power supply, and I'm reading 29.9 on the DC load here, so that's pretty good. All right, so 29.9, no current. I'm going to change the voltage on the output of the power supply. Oh, I guess you want to see what we're reading on the front pins, which is where we are actually reading from. So there we go. So 30.012, we're reading 29.99. I think that's pretty accurate. So let's change the power supply to 10 volts. And I'm reading 10 volts exactly on the front of here as well. Reading 10 volts pretty much exactly on my Keysight multimeter as well. So that's great. Now let's start cranking some amps up, shall we? And I'll read off what we're getting on the power supply as its output current, because that will be close enough. So let's go up to 250 milliamps. Even with a 10-turn pot, it's a fine adjustment. That's probably close enough. 251.1. The power supply it gives me an output reading to about 0.1%, and it's reading 251 milliamps. And I've got 251, 252 on here, so that's pretty good. I'm reading 9.7 here, even though I'm reading a 9.9 up there. But remember, we have the 1 ohm resistor plus any cable resistance in the loop as well. That's going to mess things up a bit. So I'm just going to use the meter. So 9.734. So 9.72. That's pretty accurate. Let's up the volts to 30 volts just to make sure we get a decent load on here. Okay, I've changed it to read 30 volts, so we've got 29.73 on the front of the panel meter, and on the Keysight we're reading 29.74, 29.73, so that's pretty good. Alright, that's 250 milliamps. Let's start cranking this up a little bit. Let's go to 1 amp. Alright, let's just go just below 1 amp, 9.9, because we're still reading down to microamps here. Let's just change this one. Yeah, 9.9, so 995. And I've got 994 on the power supply, so that's pretty good. And if I look at the oscilloscope, you can see that it's pretty stable. I can't see any noise on there being generated by the fan or anything like that, so that's pretty good. So now let's up the current now. It's going to switch ranges now on us, of course. Let's go up to 2 amps. Sorry, can't go to 2 amps at the moment because my power supply is limited. Let's go to 1.5, which it is able to supply. 1.499, and I've got 1.498 up on the Keithley power supply output. So that's pretty good. We've got 28.4 here, which of course we will be dropping about 1.5 volts plus cable resistance, because we've got the 1 ohm shunt resistor outside so that we can measure things with the oscilloscope. And if I put the multimeter on, we've got 28.41 and we're reading 28.40 on the panel meter. So that's more than accurate enough. Okay, so I've just switched to the 6-volt output of my Keithley triple channel power supply, and the reason for that is so that I can actually up this to a full 5 amp load. So let's crank it back up now and see where we get to. So let's go up to 1 amp. We've already done the low end. Alright, so that's 1 amp coming out, and it says 0.999 on the Keithley triple channel power supply on the 6-volt rail. We've actually got 6.1 volts actually static coming out of there, and we've got 5.03 on the front of this DC load. But let's just check with the Keysight multimeter and see. So 5.04, 5.03, that's close enough for what we're doing. So let's crank it up now to 2 amps. Okay, so that's 2 amps now. And we've got 2 amp 1.998 showing on the Keithley, and our volts, if we get our volts agreeing still to make sure there's no internal interference, 398, and we've got 396, so it's still within a couple of digits of the bottom end there, so that's good. Let's crank this up now to 3 amps. Oh, 2.90, we got 2.91 on the, well, 2.91, 2.92 on the Keithley. We got 3 amps there, and we got 2.997 shown on the Keithley power supply, and we've got 2.998 shown on the current sense output of this. So that's good. Let's go up to 4 amps. All right, 4.001, and we have 4.002 on the key 3 power supply, so that's good. And we've got 1.85 volts reading and 1.85. Of course, we're dropping 4 volts now across our shunt resistor outside here, which is getting quite hot now. What I will do is I only want that on there for the AC checks that we're going to do later, so we can hook up the oscilloscope. So I'm just going to disconnect it for the moment, and we'll hook the power directly to the current shunt so we get the full voltage. There we go. That'll be a little better for us. Alright, so that's reading 4.85. We've got 6.1 up on top on the key 3 power supply, but let's connect the keysight meter and see what we're reading. So 5.88, and I'm reading 5.85, so that's still pretty accurate for the volts there. So it just shows that we're actually now dropping quite a bit of volts across the wires coming out of the key 3 power supply. So let's go up to 5 amps. All right, that's the top. So 4.95 is the top there. I haven't put a trimmer on the DC voltage standard, so it's probably reading just a fraction low. And I didn't use the precision Vichy resistor droppers because I want to save those for when I build the computer version of this. So what I did was I just matched up some 5% resistors, selecting them out of my bin, so that's probably why it's a little bit out on the high end. But as long as you can measure what you've got, I mean, even this is still close enough. It's within 1% of 5 amps, and that's probably good enough for what you would normally use. We've got, let's have a look, 5.82 volts reading on the key site. We've got 5.78, so within 0.4 of a volt difference between the two of them, which is pretty good. It's the least significant digit. And the current is 4.95 amps, and I'm reading 4.96 amps up on the key 3 power supply. So I know the shunt at 5 amps internally on that panel meter is going to be getting a little bit warm right now. I don't know how, this is 5.5, 25 watts at the moment, and holding the heatsink on the back of this, it is not warm at all. It's marginally above ambient, but of course that's only 25 watts that we're dissipating here. What we had before was a lot more with the 1.5 amps. That was 45 watts we were dissipating with the 30 volts at 1.5 amps. And this will actually let you go up to 60 volts as well if you want to. So anyway, that's the DC voltage checking done. It looks like it's behaving quite well. I might put a trimmer on that output, but really, to be honest, it's not that big a deal. So just crank the current down a little bit. So now we're going to switch to the Arbitrary Waveform Generator and have a look from a response time perspective on the oscilloscope, see how well it works. So what we have here now is a 10 Hertz square wave being fed into the Arbitrary Waveform Generator input of the DC load, and it's got a 750 millivolt offset, which would set 750 milliamps as the medium for the current drawn. But I've got a 1 volt peak to peak square wave signal, which is basically switching it up and down by 500 millivolts on each, 500 milliamps on either side of that. And as you can see there, it's switching quite well, but of course that's only 10 Hertz, so it's difficult to see how well the rise times are. So let's increase it to something like 100 Hertz and see how we do. Okay, that's 100 Hertz. That's the leading edge of the pulse turning on, and it's at 40 microseconds per division. So you can see here that we're going from 1 amp rise, and we're doing it in about 40 microseconds, to, you know, because normally your rise time is measured between 10 and 90%. So I'm being a little generous here, and basically it's you know, 1 division is, I'm almost at the top here. It's 40 microseconds from here to here. So that's pretty good. Let's have a look at the tail end for the drop. So there's the tail end of the same waveform with a 40 microsecond per division. It's a little slower coming back down again, but it's still pretty good. It's about 40, 60 microseconds or something like that for the negative side of the slope. So I'm quite happy with that. Let's up the frequency to a kilohertz and see how well it's doing. You can see it's still keeping up quite nicely between the 40 to 60 microseconds, less than 60 microseconds for the full time. Let's just change the slope back to the positive side. and you can see here that we're still within about 40 microseconds on the leading edge. This is still with the same op amp as we had before, so I haven't tried switching that out yet, but that's pretty good. Now if I put a sine wave or something like that into it, so as you can see there, working quite nicely, no issues. And I think that's about it. So I know we've done plenty of testing on the bench with the breadboard and everything else. I just wanted to quickly show you this thing working as a DC load in the case and ready to go. I think my fan on the back is causing a little bit of interference with it, so even though I've got an inductor there, I'll have to have a look at that. But what I'm just going to quickly do right now is just drop in the OPA op amp and see if that makes any difference. What we have on the screen is the output using the TLC 272 op amp. 2 kilohertz input, 1 volt peak to peak with a 750 millivolt offset. And I've added on the screen, as you can see down here, the rise and fall time of the waveform, so it's measuring it consistently. And if you look at the mean rise and fall time, we've got about a 36 rise and about a 43 microsecond fall time. So that's not too bad at all. But let's just see what this other op amp that I have, which I said it was an OPA before, but it's not. It's an LM7332. And one of the things about this op amp is it actually has a 70 milliamp drive capability, so it might be able to drive the MOSFET a little bit better. Now I'm not going to start trying to change any of the other circuitry. I'm just going to drop it in and see if it makes any difference. So remember the fact that we've got a 36.5 and a 43 rise and fall time. Okay, just put the LM7332 in, and we're just waiting for the figures to settle down. See if we've got any better. Now remember we had a 36.5 and a 43, going back the other way. So 35.5 for the rise time, 35.8 is still flipping around a little bit, and a 42.5 fall time. Alright, so let's stick the TLC 272 back in, and we'll just double check that one because I forgot to write down what the figure was. Okay, that's the TLC 272 back in. We're just waiting for the figures to settle down. Before we had 36 and 43 for our figures, so let's see what these settle down to be. So I guess that's settled down now, and as you can see, the figures are almost identical. 36 rise, 43 fall, which is what we had before, and we basically got 36 rise and fall. So without playing around even more with other parts of the circuitry, I think you'll find that that pretty much covers it. It's not going to make any difference really to this, and I think for what we want it for really is, you know, being able to have massively fast transient response time measurements and things. I'm not sure in this setup whether my limitations are actually the Keithley triple output power supply, because it isn't designed for fast transient response times anyway, so it's going to be interfering with the readings. I think that my op amp based DC load here is working just fine for what I need, and so that's it. Anyway, I hope you like that, and that pretty much concludes the first of our projects in the power system series, which is the analog DC load. So look forward to the next one shortly, which will be for the main power supply and adding some automation to it, so microprocessor control with DACs and ADCs instead of just using the analog circuitry. Anyway, if you like it, give it a thumbs up. If you don't, then don't. It's up to you. But I hope you find this educational and useful, and hope you can apply it to your own projects in the future. That's it for now. See you again soon. Bye.